There are two keywords for this symposium: research infrastructure and sustainability. How can state-of-the-art research infrastructure can contribute to the sustainability of the world? How can we sustain such infrastructure? And what is the role of international cooperation there? To set the scene, we have invited three distinguished keynote speakers. The first keynote speaker is Professor Wolfgang Marquardt, Chairman of the Board of the Directors, Forschungszentrum Ulik GmbH, and Vice President of the Helmholtz Association, one of the largest research organizations in Europe. So Professor Marquardt, the virtual stage is yours now.
Thank you very much for this kind introduction. Dear Mr. President Hiroshi Matsumoto, dear colleagues in Japan and all around the world, in Europe and beyond, it's a pleasure to be here and to contribute to this symposium. I would like to share with you some thoughts on the research infrastructures at Helmholtz Association in Germany, with a special focus on the activities at Forschungszentrum Ju, the center, the Helmholtz Center I am responsible for. Let me start with a short overview on the Helmholtz Association, its research mission and strategy. Helmholtz stands for the research on grand challenges. We take a systems approach. We look at system solutions, linking all kinds of disciplines, looking at a systems problem and try to form large collaborations in order to address that problem in a multidisciplinary, sometimes transdisciplinary setting. Scientific excellence, interdisciplinarity and critical mass, and also the long-term research programs are the pillars of the systems approach we take. Helmholtz's mission can only be accomplished by using profound expertise in large-scale research infrastructures, and this is research with and research on infrastructures. That means in very many cases, Helmholtz builds, designs, builds, and also operates research infrastructures for Helmholtz researchers and researchers in Germany, in Europe, and all around the world. Our mission is to create impact beyond science, beyond scientific publications, and that means our knowledge has to penetrate and should reach really society by and large, economy, but also society in more general terms. Helmholtz is supposed to provide a highly attractive environment for talents and brilliant brains. A very large number of our scientific staff comes from abroad. And Helmholtz understands itself as a prime strategic partner at the local, national, and also international level. Let us look at the map of Germany and the bird's eye view of Helmholtz activity by and large. Helmholtz runs research in three research fields. They are named energy, earth and environment, health, aeronautics, space and transport, matter, and information. And these terms, I think, speak for themselves, and I don't want to dwell into the details here, but would like to refer your attention to the distribution of the Helmholtz Center on the map of Germany. You can see here these colorful symbols. Each of them stands for one of the 18 Helmholtz centers all around Germany. In total, there are roughly 44,000 employees working for Helmholtz. Out of those, there are about 37, say 40% of scientists, roughly the same number of people who are supporting the research technicians, coordinators, and so on. And the total budget is about 5.3 billion euros. Let us zoom in to Forschungszentrum Ju, which is here in the very west of Germany, close to the borders of Belgium and the Netherlands. So you can say it's in the heart of Europe, really. At Jülich, we have about 6,800 employees. 2,700 of those are scientists, doctoral students, trainees, and the others are support staff, basically. And also we are running a project management agency for the government. We have a quite flat organization, 11 institutes in 4 of the 6 research fields, which I have been presenting before. We are active in energy, matter, information, and earth and environment. Our annual budget is about 800 million. This little photograph in the middle shows the campus situation. This is basically where most of our staff is located. 5,500 people about are working here on that campus. It was founded in 1956 as a nuclear research center and has changed quite a bit over the years until now. What are we doing at Jülich? We have 3 strategic areas, and they are tightly linked by simulation and data science approaches. We aim at penetrating with simulation, data science, machine learning, and modern analytics techniques all the research activities we are carrying out. So that's kind of the organizing center, the linkage of all the activities we are carrying out. Let me look at the upper left part of the picture. This is our activity in information. This is a quite interesting and I think unique setting. It constitutes of information technologies originating from solid state physics and material science, but aiming at future computing systems, including quantum computing, as well as neuromorphic computing, and aiming at sustainable, at highly efficient, energy efficient, not only performant computing systems of the future. Then there is a branch of neuroscience aiming at understanding the function and dysfunction of the brain. And the translation of the research results not only goes to clinics, but also fuels basically the information technology research, for example, in neuro-inspired algorithms for learning, or in neuro-inspired hardware architectures for low energy computing systems with a particular emphasis on machine learning applications. And then there is a high performing computing competence center with a world-class computing center. In the energy area, we focus on renewable energies. This is embedded in climate research with a focus on atmospheric research, and we are embedding our renewable energy research in the socioeconomic system, looking at the German grid and also the European grid. And last but not least, the smallest part of our activities is bioeconomy. This basically spans the scientific activities along the value chain, from the field, from the production of plants, plant sciences, agro sciences, to biotechnology and synthetic biology, in order to produce materials, in particular from these biogeneous carbon sources. Sustainability in research infrastructures, or in research as a whole, obviously gaining knowledge, contributing to a sustainable world is basically the essence today of modern science. In order to do that, we have to synergistically use and also interrelate our research equipment with the research topics to amplify real effectiveness. That means a close interaction between those who operate the machines and build the machines and those who use these machines. In many cases, different types of research equipment, large-scale research equipment, fuel the progress in a certain research topic. The operation of that research equipment has to be resource efficient. Think of computing or large accelerators. Energy efficiency is an important issue here, but also the provision of remote access and the management, the fair management of the research data, providing them to a large user community beyond those who have carried out the experiments, is part of that sustainable operation of a research facility. Capacity building often happens around and at user facilities. This is the point where students and researchers from all around the world meet and exchange their experiences, but where they also train people on the machines, on the equipment, in order to use them to the best possible case for their problems. In the best case, we would like to address with each of the research infrastructures all these dimensions of sustainability. That's our aim. And I think we at Ulik, with our multi-thematic and highly integrated research approach, offer quite favorable conditions and possibilities for doing this. Let me dwell into one particular problem where or area where I take a little bit more time to illustrate what that means, linking these different dimensions of sustainability. And this is high-performing computing in Jülich. That started very early on when the first large-scale computers, powerful computers in the 1970s became available. Jülich decided to pick that up, driven by, at that time, still the materials research focus and the nuclear energy focus. Today, we run a modular pre-exascale computer system. Modular is referring to an architecture which has been developed at Jülich together with partners, vendors, hardware and software vendors. And basically, this modular system combines different types of computing systems, computing nodes, in order to match to the best extent possible the requirements of a certain application to gain performance at the highest level, and at the same time reducing the energy demand for a certain large-scale computational problem. And one idea we are following at the moment is not only using GPUs, CPUs, and FGPAs as modular components of the modular computing system, but also integrate quantum computing nodes and also neuromorphic nodes. We started up a quantum computing user facility, Ulik, a platform which provides various quantum computing facilities, emulators, software simulations, but also live quantum computing systems. One is a D-wave annealer, one of the most powerful annealing system of D-wave, which we just put into operation recently on site, and that's the first and the only system of that kind outside the limits of the D-Wave company itself all around the world. So deep integration of quantum computing with that modular high-performance computing environment is the problem we are currently working on, and we are quite advanced already. We develop quantum algorithms, protocols, tools, and prototypical use cases together with the users who are accessing the system remotely by a cloud-based service. And CASA is basically a structure, an organizational structure, making sure that domain experts and computational experts team up in certain so-called simulation and data labs in order to advance the state of the art in a scientific discipline using the latest and the frontier algorithms and methods on the high-performance computing systems. Yeah, Jules is one of the, well, I was too fast. Yeah, Jules is one of the most powerful systems all around the world, the most energy efficient supercomputer in the highest performance class. I don't want to dwell too much into these characteristics. What I would like to stress is that we use the waste heat from the cooling system of the supercomputing. The exascale computer, which we are planning to build in Ulik, takes about 20 megawatts and produces quite some waste heat. And we have, or we are preparing, we have prepared to use that waste heat as a heating system. You see here a little photograph of the plumbing, and this map here is the supercomputing center, and the buildings around, these buildings which I mark here, these buildings are basically supplied with hot water and heat for room heating and hot water. What are we using this system for? Well, in many scientific fields, I pick here Earth systems modeling, linking, I think, very nicely to sustainability. The contributions to the IPCC report, which is published every 7 years, some of them at least have been making use of our computing systems. The basis for the projections are the so-called CMIP simulations, where basically different models are run and compared. About 10 to 20% of the computing time on Jules, on the Jules and Jules booster system is used by the Earth systems modeling community. Our part is not only contributing to the models with our atmospheric science team, but we are also supporting teams from different centers to develop performant and energy efficient models for these demanding tasks. The resolution, the duration, and the complexity of the problems requires optimizations in all directions. And this is facilitated, obviously, by modern energy efficient architectures, GPU-based architectures to a large extent. Unnecessary data transfer has to be prevented, and the model output and data storage has to be optimized in order to contribute to efficiency and thus to sustainability. What we feel is necessary, and infrastructures are basically a driver for that, is to have convergence between various fields. And this is what we definitely emphasize in all our activities. But here again, looking at the research focus information, this little sketch gives you an example how we link neuroscience, high performance computing, and information technology. I was referring to this a little bit before. Neuroscience and information technologies is closely related by inspiration from neuroscience to information technologies, but also information technologies contributing to neuroscience. For example, probes in the brain to stimulate or to measure brain activity. Obviously, this is micro nanoscale engineering, which is necessary in order to have these brains implants in these probes implanted in the brain. Then high performance computing and information technologies, the quantum computing system we are developing will be integrated with a high performance computing system. And that's a gate level computer we are working on as part of a European project, but also that D-Wave machine will be integrated here with a high performance computing system. So again, a close interaction between the two. But as you can imagine, high performance computing is the driver basically of developing new materials, new information technologies without simulation, multi-scale from the first principles up is today part of the routine business. And again, neuroscience is using to a very large extent high performance computing in order to dwell into the details of the function of the brain. Let me conclude. Research on and research with large-scale infrastructures is at the heart of our activities. I have been elucidating this principle just with one example from the Ulik research infrastructure portfolio. That was the high-performance computing example here. I'd like to make a few remarks on the other facilities we operate. Here, this little icon stands for the electron microscopy and spectroscopy facility, a premier, really worldwide, unique and premier facility, operating 7 or 8 at the moment first-class electron microscopies. Cryo-EM has been including in the last years, and we are extending that suite of systems by another 4 microscopes, which we have ordered to really become the premier and the leading user facility in the world, with applications in hard matter, dedicated to information and energy technologies in the first place, but also to the life sciences and to the soft matter community, in particular those communities who make use of cryo-electron microscopy. Another example, this little figure here, refers to neutron probes, neutron science. At Ulik, we have been operating reactors in the past. Now we are operating best instruments at best sources around the world, in particular in Germany and Europe, at Munich. This is an outpost of Ulik, where our staff is operating instruments around the Garching reactor. Then we are engaged in the European spallation source at Lund, which is being ramped up at the moment, and we are also engaged in ILL in France, a high flux reactor for neutron science, in addition to the national facility at Munich. This example here is a world-class gigahertz NMR spectroscopy device, which is the flagship instrument in a larger facility with roughly 5 to 8, depending on the size you count. So NMR spectroscopes for basically elucidating the structure of biomolecules, with applications in particular in brain-related issues, but also in related areas like in recent times, the question of, basically questions related to immunology and vaccination. These 2 facilities from atmospheric science, or this is a facility from atmospheric science, an atmospheric chamber to simulate basically in an experiment, in a real experiment, atmospheric chemistry situations. Yeah, this is just a glance to close here with on a few other large-scale research infrastructures we are operating here at Ulik. Thank you very much for your attention, and I was happy to contribute. And if you have any questions, let me know either here or by approaching me directly. Thank you very much.
Thank you very much, Professor Marquardt, for the comprehensive presentation.